the stillness of night, a stone falls through the atmosphere. It burns, it fractures, and it lands upon the earth with a silence more ancient than the planet it strikes. To the unknowing eye, it is nothing but rock, dark, lifeless, unremarkable. Yet hidden within its silent weight lies a memory older than earth, older than the sun, older than the sky itself. For some of these stones carry within them the ashes of stars. Stardust, not metaphor, but fact. Tiny grains, crystalline fragments forged in furnaces of suns that lived and died billions of years ago. They drifted through interstellar space, endured shock waves and cold, and were gathered in the birth cloud of our solar system. When the planets formed, most of this memory was erased, melted and remade, but not all. Some grains survived. They became locked in meteorites, preserved as time capsules. They are the last unbroken voices of stars that no longer shine. What does it mean for matter to remember? How can a stone, inert and silent, carry the story of nuclear fire, of fusion and collapse, of stars that breathed light into the void? These fragments hold isotopes unknown to Earth, signatures etched by stellar furnaces that burned long before our world existed. And if stones can remember suns, what of us? The calcium in bones, the iron in blood, the oxygen in every breath. All were born in stars. Perhaps we, too, are living archives, walking testaments to stellar death and rebirth. This is the mystery. The stones that fell from the sky, carrying within them the memory of suns. The stones that remind us that even matter can dream. Long before laboratories and telescopes, long before equations gave form to the heavens, people looked to the sky and watched stones fall. In the silence of night or the blaze of day, streaks of fire carved across the atmosphere, leaving trails of awe and fear. To ancient civilizations, these were omens, messages from gods or ancestors, fragments of celestial will descending upon the earth. They were revered, feared, and sometimes worshipped. A skystone was not just rock, it was a messenger in Mesopotamia. Meteors were interpreted as signs of divine judgment. In Greece, Aristotle argued that they were terrestrial vapors igniting in the air, mere atmospheric phenomena. In China, records spanning thousands of years describe falling stars and firestones, woven into dynastic chronicles as portents of change. For millennia, humanity saw them not as cosmic artifacts, but as signs of destiny, burning. Symbols written briefly across the sky. The transition from myth to science was slow. Even into the 18th century, respected scholars doubted that stones could fall from the heavens. The earth was thought to be separate from the heavens, the celestial realm perfect and immutable. To suggest otherwise seemed absurd. Meteorites, when found, were dismissed as lightning-struck rocks or volcanic debris. But then came the undeniable. On April 26, 1803, in the French town of Les Galles, the sky erupted. A thunderous explosion shattered the calm, and thousands of stones rained down across the countryside. More than 3,000 fragments were collected, scattered across fields and villages. The event was witnessed by scores of people, too many to dismiss. Jean-Baptiste Biot, a young physicist sent by the French Academy of Sciences, meticulously documented the fall. His report confirmed what had long been ridiculed. These stones came not from Earth, but from space. The heavens were not unchanging. They could, quite literally, fall into our hands. With that realization, meteorites became more than curiosities. They became samples. Physical evidence of the cosmos delivered to Earth. Scientists began to study them with the tools of chemistry and mineralogy. By the late 19th century, advances in spectroscopy, the science of reading light, allowed astronomers to compare the composition of meteorites with that of stars. For the first time, it became clear these were not random stones, but records of cosmic processes. They bore the fingerprints of celestial furnaces. Yet the true revolution came in the 20th century, when scientists turned to isotopes, the subtle variations in atoms that reveal their origins. Atoms of the same element can have different numbers of neutrons, forming isotopes with distinct signatures. These isotopic fingerprints act as tracers, telling scientists where and how an atom was forged. In the 1950s and 60s, a new picture began to emerge. Meteorites were not just fragments of the early solar system. Some contained material, far older grains that predated the sun itself. It was Edward Anders and his colleagues at the University of Chicago who pushed this frontier forward. Anders was fascinated by the question of origins, of the solar system, of Earth, of the elements themselves. Alongside him, Ernst Zinner, a meticulous experimentalist, began to probe meteorites with unprecedented precision. Using mass spectrometry, they found isotopic anomalies that could not be explained by any process occurring within the solar system. The ratios of carbon, oxygen, and silicon in certain tiny grains were utterly alien. They did not match the sun, the planets, or even the nebula from which the solar system formed. Instead, they bore the unmistakable signature of stars long gone. These grains had formed in stellar atmospheres, condensed from the cooling winds of red giants, or forged in the violent ejecta of supernova. And somehow, against all odds, they had survived. They had traveled across the galaxy, drifting for millions or billions of years, until they became part of the cloud that collapsed into our sun and planets. Locked within meteorites, they were preserved as time capsules, fragments of other suns that once burned across the galaxy. The first such pre-solar grains identified were silicon carbide crystals, microscopic in scale, yet carrying within them a record of stellar processes billions of years old. Later came graphite grains, tiny diamonds, and oxides. Each type pointed to different stellar forges: carbon stars, red giants, supernova. The evidence was undeniable. The meteorites in our museums and laboratories were mosaics of stellar memory. They were archives, holding within them the stories of stars that lived and died before the Earth had ever existed. The revelation was staggering. It shattered the old assumption that the birth of the solar system had erased all prior history. For decades, scientists had believed that the dust and gas forming the planets had been completely homogenized, mixed into a uniform soup by the violence of collapse and accretion. But these grains had survived intact. They had endured the chaos of star birth and planet formation, slipping through cosmic violence without losing their identity. To hold a meteorite was suddenly to hold a relic of cosmic ancestry. Within its dark matrix lay crystals older than the sun, carrying isotopic whispers from stars extinguished long before our world began. They were not just scientific specimens. They were fragments of history written in the language of atoms. The scientists who uncovered this truth felt its weight. Ernst Zinner once described pre-solar grains as messengers from ancient stars. They were not theories or equations, but physical evidence, tangible proof of stellar death and rebirth, delivered into human hands. Each grain was a survivor, a traveler across unimaginable distances and timescales. Each was a witness to cycles far beyond the span of human history, and with their discovery, the central mystery deepened. If these stones hold the memory of suns, what else might they reveal? Could they tell us the story not only of stellar life and death, but of the galaxy itself? Could they help us trace the chain of matter that led from ancient stars to the rise of Earth and even to life? The discovery phase had come to an end, but the true journey was only beginning. Scientists now knew that meteorites contained fragments older than the solar system, relics of suns extinguished billions of years ago. The challenge that followed was to read them, to unlock their atomic memories, to listen to the voices of stars preserved in stone. The age of cosmic archaeology had begun. It is one thing to imagine that the universe is ancient, to trust equations that place the age of the cosmos at 13.8 billion years. It is another thing entirely to hold in one's hand a piece of matter that remembers that history. For most of modern science, meteorites were regarded as primitive fragments of the solar system, relics from 4.6 billion years ago. Old, yes, but no older than the sun itself. The revelation that inside them lay grains predating the solar system shook the foundations of cosmology, geology, and astrophysics alike. The first shock came from isotopic analysis, when researchers measured the ratios of carbon, oxygen, nitrogen, and noble gases in certain grains. They found values unlike anything in the solar system. These isotopic signatures were fingerprints of stellar nucleosynthesis, the process by which stars forge elements in their cores and scatter them into space through winds or explosions. The patterns could only be explained if these grains had been born in other stars, long before our sun had ignited. The implications were staggering. The accepted narrative had been that during the birth of the solar system, the cloud of gas and dust collapsed and heated so violently that any trace of earlier history was obliterated. Everything, every planet, every asteroid, every grain of rock was thought to have been remade, melted, and reformed into a homogenized whole. But these tiny crystals stood in defiance of that story. They had endured collapse, heating, and turbulence, yet preserved their original isotopic memories. This was not just a refinement of detail, it was a paradigm shift. The solar system was not a blank beginning, but an inheritance. The material that gave rise to Earth and its life did not emerge solely from a featureless nebula. It was composed of fragments of stars, survivors from older generations. Our solar system was not an isolated genesis. It was a continuation. The presence of prosolar grains inside meteorites forced scientists to reconsider the resilience of matter. Stardust is fragile. Formed in stellar winds or the debris of supernova, the grains are microscopic, some no larger than a virus, others no wider than a red blood cell. How could such delicate crystals survive a supernova's blast, the icy vacuum of interstellar space, the collapse of a giant molecular cloud, and the violent accretion that built planets? According to earlier models, they should not have. And yet there they were, silent proof that the cosmos carries its own memory, written into the most fragile of stones. The emotional weight of this realization cannot be overstated. For generations, humanity had believed that the sun was the beginning of our story. To discover matter older than the sun was to discover that our story began elsewhere, in stars that lived and died before our solar system existed. To hold a meteorite was no longer to hold a simple rock. It was to cradle the ashes of suns. It was to feel, in the palm of one's hand, the remnants of nuclear fire. This was the second great shock. the recognition that the very atoms within us shared this ancestry. The same isotopic anomalies found in meteorites remind us that the calcium in bones, the iron in blood, the oxygen we breathe, all were forged in stars. Carl Sagan's famous phrase, "We are made of star stuff," was not poetry, it was literal truth. But the discovery of presolar grains took that truth further. Not only are we made of star stuff, but the stars themselves can be touched, their remains studied directly, their isotopic whispers held in stones that fall from the sky. Scientists struggled with disbelief. Could the data be an error of instrumentation? Were the anomalies artifacts of measurement? For a time, skepticism reigned, but repeated analysis across multiple laboratories and multiple meteorite samples confirmed the findings. The isotopic ratios were real. The grains were not products of our solar system. They were older, much older. The field of cosmochemistry had been forced into a new era. Edward Anders compared the discovery to archaeology, but at a cosmic scale. Just as ancient pottery preserves the fingerprints of vanished civilizations, these microscopic grains preserved the fingerprints of vanished stars. The analogy was apt, for here, in a handful of meteorite dust, lay the ability to reconstruct the nuclear history of the galaxy. The shock extended beyond geology and chemistry. Astrophysicists had to confront the inadequacy of existing models. Stellar nucleosynthesis, the theory describing how stars build elements, had been robust in its predictions. But now, with pre-solar grains in hand, scientists had test samples against which to compare theory. Some isotopic patterns matched expectations beautifully, others did not. Certain grains carried isotopic anomalies that could not yet be explained, hinting at nuclear reactions within stars that models had overlooked. One especially striking case came from noble gases, xenon, krypton, neon, trapped within meteorite grains. These gases showed isotopic patterns unlike any seen in the Sun or planets. They bore the signature of the R process, the rapid neutron capture process that occurs in supernova or neutron star collisions, forging the heaviest elements in the universe. Here, in meteorite fragments smaller than a grain of sand, was direct evidence of explosions unimaginably distant in space and time. Explosions that had seeded the galaxy with the building blocks of matter long before Earth was born. For scientists, the implications were twofold. First, the solar system is a mosaic of stellar memories, not a blank canvas. Second, the galaxy itself is a crucible of recycling, where stars live, die, and give their ashes to future generations. The pre-solar grains were more than scientific curiosities. They were proof of cosmic continuity. And yet, with proof came paradox. If such grains could survive, how many more lay hidden? If some meteorites held grains older than the solar system, did Earth itself? Could fragments of pre-solar stardust still exist, locked deep within our planet, forgotten beneath oceans and continents? The thought was staggering, that the ground beneath our feet might hold memories of suns long dead, waiting to be uncovered. The discovery unsettled the boundary between the eternal and the fragile. A star dies in fire, its matter cast into space. And yet, from that violence, something survives. A crystal, a fragment, a whisper of isotopes. Across billions of years and unthinkable distances, the memory remains. A star is gone, yet its story endures in a stone that can be held, weighed, studied. For humanity, This was a revelation both humbling and profound. Science had not only proven that we are made of stars, it had shown us that stars leave their signatures in matter itself. That memory can be physical, etched into the atomic lattice of crystals older than our sun. To touch such a grain is to touch time itself, to hold in one's hand the last breath of suns. The shock still reverberates in every meteorite that falls, in every fragment collected from deserts or ice fields. There may lie the record of stars beyond number, each grain a memory, each stone a vessel of suns, and the mystery deepens. If these stones hold the memory of suns, what other truths lie hidden within them? The first revelations of pre-solar grains were like opening an ancient book whose language was only partly known. Scientists could read fragments of meaning, but the full story of these grains demanded sharper tools, deeper patience, and the courage to chase mysteries into realms of almost impossible precision. The stones had spoken, but quietly. To truly hear them, science would need to listen, atom by atom. The 1980s and 1990s saw the emergence of instruments capable of probing these grains at the level required. Among them, secondary ion mass spectrometry, SIMS, became the cornerstone. The principle was deceptively simple. Bombard a sample with a focused ion beam, dislodge secondary ions, and analyze their mass with extraordinary accuracy. In practice, it was delicate work, pushing the boundaries of detection. With SIMS, scientists could measure isotopic ratios in grains no larger than a micron. A fragment invisible to the naked eye became an atlas of stellar history, and the results were astonishing. Within meteorites, such as the Murchison carbonaceous chondrite, grains of silicon carbide revealed isotopic ratios pointing unmistakably to red giant stars. In these swollen, dying stars, nuclear fusion forges carbon in abundance and stellar winds carry it outward, where it condenses into tiny crystals. These grains drift into interstellar space, becoming seeds of memory. To isolate such a grain from a meteorite was to isolate a crystal that had once condensed in the breath of a dying sun. Other grains told stories of greater violence. Graphite crystals and nanodiamonds bore isotopic signatures pointing to supernova. These explosions, the catastrophic deaths of massive stars, scatter elements across the cosmos, forging iron, nickel, and the heavy elements that cannot be created in ordinary stars. Within some presolar grains, isotopes of oxygen and neon revealed patterns consistent with explosive nucleosynthesis, the furious nuclear alchemy that occurs in a star's final heartbeat. To hold such a grain was to hold the debris of a stellar detonation, a relic of cosmic violence frozen into a crystal structure. Still others carried the signature of asymptotic giant branch stars, AGB stars, the late evolutionary phase of sun-like stars. In these bloated, unstable stars, thermal pulses create conditions for forging elements like aluminum, silicon, and S-process isotopes, atoms built slowly, neutron by neutron. Oxide grains extracted from meteorites displayed just these isotopic patterns, their oxygen ratios whispering the story of stars that swelled, pulsated, and shed their outer layers into the void. Every grain became a messenger, each carrying the fingerprint of a specific stellar process. For the first time, scientists were reconstructing stellar life cycles, not by watching stars through telescopes, but by dissecting the dust those stars had left behind. It was forensic astronomy, cosmic archaeology performed not in the sky, but in the laboratory. The deeper the investigations went, the more puzzling anomalies emerged. Noble gases trapped within nanodiamonds showed ratios unlike any predicted by existing models of stellar nucleosynthesis. Some silicon carbide grains displayed isotopic compositions so unusual that they seemed to come from stellar environments. Not yet fully understood, laboratory experiments attempted to recreate nuclear pathways to trace how isotopes could emerge from reactions inside stars. Again and again, the meteorites revealed gaps in theory, as if the stones were challenging science to refine its understanding of stellar alchemy. This raised another profound question: survival. How could grains so delicate, formed in the tenuous atmospheres of stars or the chaos of supernova ejecta, persist across the ferocity of interstellar travel? For millions or billions of years, they drifted through a galaxy rife with radiation, collisions, and turbulence. They endured the collapse of the molecular cloud that birthed the sun, a process expected to heat and crush dust into anonymity. Yet somehow, against probability, they survived intact. Some theories proposed protective mantles, coatings of carbon, or ices that shielded grains from destruction. Others suggested rapid ejection from stars, hurling grains into interstellar space before they could be destroyed by heat. Still others invoked magnetic fields, turbulence, or sheer luck. None were fully satisfying. The survival of presolar grains remained as mysterious as their origins. As instruments improved, the investigation widened. Nano-CMS allowed even greater precision, mapping isotopic compositions across single grains with submicron resolution. Atom probe tomography pushed further still, slicing grains atom by atom, reconstructing their structure in 3 dimensions. What emerged was a picture of extraordinary resilience. Crystals that had endured journeys across the galaxy, yet preserved their atomic signatures as if frozen in time. The data began to feed into a grander narrative: galactic chemical evolution. Every star contributes to the chemical enrichment of the galaxy. Hydrogen and helium, born in the Big Bang, are the canvas. Stars paint upon it with carbon, oxygen, silicon, iron, and beyond. Each generation enriches the interstellar medium, and from that medium, new stars and planets form. Presolar grains are not merely curiosities. They are data points in this grand cycle. They are the physical evidence of how the galaxy builds itself. Some grains date back more than 7 billion years. Older than the sun by billions, they suggest. A galaxy rich in stellar death and rebirth before our solar system ever formed. Their isotopic fingerprints are the threads of a cosmic tapestry stretching back through countless generations of stars. Without them, our models of galactic history would be abstract. With them, the story becomes tangible. The deeper investigation revealed another layer of intimacy. These grains connect directly to us. The calcium in bones, the iron in blood, the oxygen in lungs, all forged in stars. But unlike the homogenized elements of Earth, presolar grains are direct survivors. They are the unblended, unbroken remains of ancient suns. When we study them, we are not merely confirming that we are made of stardust. We are touching the original dust itself, the unedited memory of stellar life. This realization infused the science with philosophy. The grains were not alive, yet they carried memory. They were not conscious, yet they bore witness. In them, the past was not abstract, but preserved, written in isotopes and crystalline structures. A dying star, billions of years ago, expelled its last breath. That breath condensed, drifted, traveled across the void, and came to rest inside a meteorite. Billions of years later, on a small planet orbiting a modest star, human beings uncovered. It, studied it, and listened to its silent story. And the story was vast. Stardust grains revealed not only the fates of individual stars, but also the hidden processes shaping galaxies. They hinted at nuclear reactions unaccounted for, at survival. Mechanisms not fully understood. They connected cosmic events to tangible evidence in our hands. They blurred the boundary between the ephemeral and the eternal. The investigation deepened, but so too did the mystery. For every isotopic anomaly explained, another arose. For every stellar process identified, another remained elusive. The grains seemed to guard secrets even as they revealed truths. By the close of this phase, one thing was certain: pre-solar grains were more than curiosities. They were keys. They opened doors to stellar physics, galactic history, and the intimate connection between humanity and the cosmos. Yet each key also revealed locks still unopened, mysteries yet unsolved. The stones had been cracked open, their grains isolated and analyzed, but their memory ran deeper than expected. If they could survive so much, stellar death, interstellar travel, planetary birth, then what other stories did they contain? What enigmas remained hidden within their crystalline silence? The deeper investigation had not ended the mystery. It had only expanded it. Discovery breeds wonder, but it also breeds unease. Each grain that was uncovered, each isotopic ratio that was measured, pushed the mystery further, not closer to resolution. For, if pre-solar grains were rare, fragile anomalies, they might have been dismissed as cosmic accidents, curiosities carried through the violence of creation by sheer chance. But they were not rare. They were abundant. The first paradox was survival in numbers. Within certain meteorites, pre-solar grains make up measurable fractions, thousands of parts per million. This may sound small, yet in cosmic terms, it is overwhelming. It suggests not a single survivor, but an entire population of stardust grains enduring against astronomical odds. The expected furnace of solar birth, the collapse of the molecular cloud, should have annihilated every trace. Instead, billions of ancient grains slipped through untouched, carrying with them the memory of suns older than the sun. Why? The question haunts cosmochemistry. Models of stellar birth predict a far more thorough homogenization. If pre-solar grains survived, then our understanding of how molecular clouds collapse, heat, and mix may be incomplete. Perhaps the cloud was gentler than imagined, or the grains more resilient. Perhaps pockets of the collapsing nebula shielded them, preserving their fragile cores while chaos raged nearby. Yet no theory has fully explained their abundance. Then came anomalies, stranger still. Some silicon carbide grains displayed isotopic patterns inconsistent with known stellar processes. Their ratios of carbon and nitrogen, their traces of heavy elements, pointed to nuclear reactions beyond the standard models of red giants and supernova. Certain grains bore excesses of rare isotopes: titanium 50, calcium 44, xenon H.L. Isotopes that standard nucleosynthesis could not easily account for. They seemed to be fragments of stellar environments not yet understood, whispers of processes occurring in conditions we had never modeled, or perhaps never witnessed. Supernova grains, in particular, carried riddles. Some bore isotopic signatures of explosive oxygen and neon burning. Others carried noble gas isotopes in ratios so exotic they implied mixing of stellar layers in ways our models did not predict. A supernova, once thought to be a relatively understood engine of element formation, now appeared far more complex, a crucible with processes, we had only begun to glimpse. The paradox deepened with evidence of unexpected chemistry. Within some grains, elements appeared combined in ways unstable under laboratory conditions. Traces of graphite, interlaced with isotopes pointing to supernova, suggested that even in chaos, order emerges, structures forming in explosions, violent enough to unmake worlds. How could carbon crystals condense within the blast of a star's death? What forces allowed stability in the very heart of destruction? Each answer gave birth to further questions. If pre-solar grains carried signatures of stellar deaths billions of years before the sun, then how complete was their record? Were these grains a representative sample of all stellar processes, or merely the survivors, the lucky few whose compositions allowed them to endure? If so, what stellar stories had been lost, erased by destruction, leaving us only fragments of truth? The enigma was not confined to isotopes. It extended to abundance across different meteorite types. Some carbonaceous chondrites seemed to harbor vast reserves of pre-solar grains, while others contained almost none. Why should the cosmos distribute memory unevenly? Did certain regions of the solar nebula preserve more stardust than others? Was there a hidden structure in the way matter was drawn into planets and asteroids? The shock of abundance and the riddles of isotopes converged into a single disturbing thought. The stones might hold more than fragments of stellar history. They might hold stories we are not yet able to read. They might conceal processes that will force us to rewrite the physics of stars. And there was another layer, one even more intimate. If stones can preserve the memories of suns, then what of us? The iron coursing through veins, the calcium fortifying bones, the oxygen feeding lungs, all are stellar relics. But unlike the homogenized matter of Earth, these meteorites hold the direct, unaltered record. They are memory in its purest form. They are what we might have been, had the solar system preserved its inheritance unbroken. This realization carried emotional weight. To hold a meteorite was no longer to hold an inert rock. It was to cradle a time capsule from before the sun existed. It was to feel, through the cool weight of stone, the silent presence of stars long dead. Human beings, ephemeral and brief, were touching matter that had seen billions of years, that had survived distances beyond imagination. The mystery was no longer only scientific. It was philosophical. If matter remembers, then memory itself may be a fundamental property of the universe. If isotopes are the script, then every atom is a letter in a story that began long before life, long before planets, perhaps long before memory as we understand it. These grains whispered of eternity, of cycles of birth and death, written not in words, but in the ratios of atoms. The escalation continued with discoveries of rare isotopes pointing to R-process nucleosynthesis, the rapid capture of neutrons. In environments like supernova or neutron star mergers, this process, essential for creating elements heavier than iron, remains poorly understood. Yet here it was, etched into grains smaller than a red blood cell. These stones were not merely archives of stars. They were archives of the deepest mysteries of nuclear physics, recording processes so extreme that they occur only in the most violent events the universe knows. And still the question returned, how? How could such delicate grains survive all? They endured violent stellar deaths, turbulent interstellar travel, the collapse of the nebula, the heat of accretion, the birth of planets. The odds of survival seemed infinitesimal, yet the reality was undeniable. Stones rained from the sky, filled with grains that should not exist. The paradox threatened to overturn assumptions about the nature of matter itself. Perhaps grains are not as fragile as believed. Perhaps interstellar space is not as hostile. Or perhaps our models of collapse, heating, and mixing are incomplete, failing to capture the subtle ways in which memory endures. Each possibility unsettled the foundations of astrophysics. By the end of this deepening phase, scientists faced a troubling realization. Pre-solar grains are not passive relics. They are active challenges. They do not merely preserve the history of stars, they confront science with the unknown, forcing it to confront its limits. They tell us that the cosmos is not yet fully understood, that even in the smallest of stones there are enigmas vast enough to humble entire disciplines, and for humanity. The implication grows ever heavier. If stones can hold the memory of suns, then we ourselves are carriers of cosmic inheritance. But unlike the stones, our memory fades. Our lives are brief, our records fragile. The meteorites endure longer than civilizations, longer than species. They hold their silence until they are found, and when they are, they remind us that the universe forgets nothing. The abundance of pre-solar grains, their inexplicable isotopes, their survival against all odds, all point to a universe where memory is woven into matter itself. The mystery is no longer whether these stones remember, it is what else they might be trying to say. The escalation was complete. What began as fragments of curiosity had become a confrontation with the unknown. Stones that fell from the sky were no longer passive. They were active participants in the dialogue between humanity and the cosmos. And in their silence, they pressed a single question upon us. Are we ready to understand the memories they hold? The stones had spoken, but not in a single voice. Each grain whispered a different origin. Each isotope carried a different memory. And so science turned to theory, to speculation, to the weaving of possible explanations, to understand how such fragments could exist, and what they truly revealed. Physicists and cosmochemists began building bridges between observation and imagination. The foundation of these bridges lay in stellar nucleosynthesis, the grand process by which stars forge. The elements, hydrogen fuses into helium. Helium, under greater pressures, into carbon and oxygen. In the cores of massive stars, layers form like the rings of an onion, each burning a different fuel, each a crucible of transformation. When the star dies, whether gently as a red giant or violently as a supernova, these elements are cast outward, enriching the galaxy. The theory is elegant, confirmed by spectra of stars and the chemical abundances of the cosmos. But pre-solar grains made this theory tangible. They were not abstractions. They were the literal byproducts, the cooled ashes of stellar fire. Red giants became the first suspects. Their slow winds and cool outer atmospheres provided conditions where carbon could condense into silicon carbide grains. The isotopic ratios matched. In these grains, scientists could see the breath of stars that had died quietly, shedding their layers into the void. Yet not all grains fit this model. Some carried isotopes formed only in the titanic pressures of supernova. Theories expanded. Supernova, it seemed, were factories of diversity. In their explosions, the rapid neutron capture process, the R process, forged elements heavier than iron, elements like gold, platinum, and uranium. Pre-solar grains, carrying traces of these isotopes, suggested that within their crystalline structures were the echoes of explosions powerful enough to reshape galaxies. Yet how grains condensed in such chaos remained speculative. Some proposed that grains formed in the cooling outer ejecta, shielded by rapid expansion. Others suggested clumps of matter condensed within the shockwave, pockets of stability amid destruction. Neither explanation was complete. Graphite grains offered further puzzles. Their isotopic fingerprints often hinted at origins in supernova. Yet graphite, a stable form of carbon, should be fragile in such extreme conditions. Why would such grains not burn, vaporize, or fragment? Theories arose that protective mantles, thin layers of other materials, may have shielded them. Some suggested rapid cooling locked them into survival before destruction could reach them. Here, speculation walked hand in hand with imagination. Other theories turned to the interstellar journey itself. How could grains survive millions of years in the radiation-filled void? Some speculated that their crystalline lattice were remarkably resistant to damage, able to absorb cosmic rays without losing identity. Others suggested that ice mantles, accreted in cold molecular clouds, offered protection. Still others invoked the possibility of magnetic shielding, with grains riding magnetic fields like ships, carried by invisible currents. The speculation extended to the birth of the solar system. Standard models suggested that the collapse of the solar nebula should have destroyed any fragile relics. But the survival of presolar grains implied otherwise. One theory proposed that the collapse was not uniform, that localized regions of cooler, denser gas shielded the grains. Another suggested that grains were incorporated into larger aggregates quickly, hidden inside pebbles and planetesimals where heat could not reach. Some proposed that turbulence within the nebula allowed mixing without complete homogenization, preserving islands of ancient memory within the maelstrom of creation. Each of these ideas carried weight, but none yet resolved. The enigma. And so speculation grew more expansive, more philosophical. If stones can remember suns, perhaps memory itself is woven into the fabric of matter. Perhaps atoms, with their isotopic ratios, are not merely the result of physics, but the script of cosmic history. Each nucleus becomes a word in a story, each grain a chapter, each meteorite a book. The universe, in this view, writes its history not in language, but in matter. Galactic circulation added another layer of theory. The Milky Way is not static. Stars live and die, casting their ashes into the interstellar medium. Clouds form, collapse, and form new stars. Over billions of years, this cycle repeats endlessly. Presolar grains are not just relics of individual stars. They are nodes in this vast circulation, particles that have traveled through multiple generations of stars. Some may have witnessed the birth of clusters now dissolved. Others may have drifted through interstellar clouds, later swept into spiral arms. Their presence in meteorites is a reminder that the galaxy itself is a living, evolving entity, recycling matter in endless cycles. Speculation also turned toward the mosaic nature of meteorites. If each presolar grain came from a different star, then each meteorite was a patchwork of stellar histories. Within a single stone, one could find grains from red giants, supernova, and perhaps even novae, each telling a different story, each bearing the memory of a different sun. The stone became more than a rock. It became a library, its shelves filled with the ashes of stars. From here, philosophy seeped into science. If matter carries memory, what of time? Could presolar grains be not only remnants of stars, but also archives of cosmic chronology? Their isotopic ratios reveal not only origins but ages. windows into epochs billions of years past. They collapse the distance between then and now, carrying the first moments of stellar death into the present. Stones, in this sense, become bridges across time, reminders that in the universe nothing is truly lost. Some speculations were bolder still. If stardust survives across billions of years, could life itself owe its origin to similar resilience? Could grains carrying organic compounds have seeded young worlds? While presolar grains are primarily mineral, their existence strengthens the idea that matter, even fragile matter, can endure across cosmic epochs. If crystalline structures survive supernova, why not carbon chains, amino acids, or precursors of biology? Such ideas remain speculative, but they underline the philosophical weight of these discoveries. Theories branched further, exploring how presolar grains might serve as tests for physics itself. If isotopic ratios defy current models, perhaps the models of nuclear fusion within stars require revision. If noble gas anomalies persist, perhaps they point to nuclear processes not yet discovered. In this way, the stones become not only memories of suns, but guides for science, pointing toward the unknown. And beneath all these theories and speculations runs a single haunting thought. Perhaps the universe forgets nothing. Perhaps memory is not the privilege of life, but the property of matter itself. Stones remember stars. Stars remember galaxies. Galaxies remember the first fire. And in each atom, in each isotopic ratio, lies a trace of that endless memory. To speculate on presolar grains is to speculate on the nature of reality. Are we merely interpreters, uncovering meanings that have always been there? Or do we, in studying these grains, create the memory ourselves, giving voice to silence, weaving story from isotope? In either case, the stones hold their truth. They remain silent and enduring, while human theories rise and fall. The speculations form a spectrum from the strictly scientific to the deeply philosophical. Red giants, supernova, nucleosynthesis, galactic recycling, all are models rooted in physics. But beyond them lies metaphor, stones as archives, matter as memory, atoms as storytellers. And in that metaphor lies a truth no less profound. To hold a meteorite is to hold the memory of suns. The stones had revealed their mystery, but unlocking their memory required more than wonder. It demanded tools capable of peering into the smallest fragments of matter, of measuring isotopes atom by atom, of reconstructing stellar histories from particles smaller than dust. To study the memory of suns, humanity needed instruments that could rival the patience of time itself. The journey began with mass spectrometry. Early instruments offered glimpses, measuring isotopic ratios in bulk samples of meteorites. But these methods blurred the signal, averaging grains together, losing the individuality that made them so precious. The revolution came with secondary ion mass spectrometry, SIMS, and later its more refined form, nano-SIMs. With these machines, scientists could aim an ion beam at a single presolar grain and eject secondary ions, analyzing their mass with exquisite precision. At last, the individuality of grains could be read. The silicon carbide of a red giant, the graphite of a supernova, the oxide of an asymptotic giant branch star, each revealed its story, etched in isotope. Nano-SIMs became the storytellers. Lens, mapping ratios of carbon-12 to carbon-13, oxygen-16 to oxygen-18, neon to xenon. Patterns emerged, clusters formed, families of grains tied to specific stellar origins. Without these instruments, pre-solar grains would remain curiosities. With them, they became archives of galactic history. But SIMS was only the beginning. Atom probe tomography took analysis deeper still. This technique could strip away atoms one by one, mapping their three-dimensional positions within a grain. It offered not only isotopic composition, but spatial arrangement, revealing how elements clustered, how crystals formed, how memory was structured at the atomic level. The first atom probe studies of pre-solar grains opened windows into formation, processes showing growth patterns, condensation sequences, and traces of environments billions of years gone. Synchrotron radiation added yet another layer. These vast particle accelerators, bending electrons to produce intense beams of X-rays, allowed scientists to probe the structure of grains without destroying them. With synchrotron light, researchers could examine the chemical bonds, the lattice structures, the subtle imperfections that marked a grain's journey through space. The non-destructive nature of synchrotron analysis meant the stones could be studied and preserved, their secrets revealed without erasure. Laboratories were not the only stage for discovery. Space itself became a collaborator. Missions like NASA's Stardust brought back samples from Comet Wild 2, capturing dust grains in aerogel collectors. Among them, scientists identified particles of possible pre-solar origin, preserved in the icy nucleus of a comet that had orbited the Sun for billions of years. Stardust proved that comets, like meteorites, were keepers of cosmic memory. Japan's Hayabusa 2 and NASA's OSIRIS-REx took the quest further, returning samples from asteroids Ryugu and Bennu. These missions brought pristine material untouched by Earth's contamination, delivering stones that carried within them the unaltered history of the early solar system. Already, isotopic analyses are uncovering traces of pre-solar grains in these samples, confirmation that the memory of suns is scattered throughout our solar neighborhood, waiting to be gathered. Future missions aim still higher. Proposals exist to capture interstellar dust directly, to sweep up particles drifting through the solar system that may never have been part of it. NASA's Interstellar Mapping and Acceleration Probe IMAP, launching in the coming years, will measure interstellar particles entering the heliosphere. One day, spacecraft may return them intact, grains untouched by solar birth, survivors of journeys across the galaxy. Yet even on Earth, fresh samples fall daily. Cosmic dust settles in the stratosphere, collecting on Antarctic snow, embedded in ocean sediments. Specialized collectors gather these particles, sieving them from earthly contamination. Among them are pre-solar grains, newly delivered from the sky, evidence that the galaxy still sows its memory upon our world. Each year, thousands of tons of interstellar dust rain down on Earth. Within it may lie grains older than the Sun, silent travelers arriving unnoticed at our feet. The frontier lies not only in collection, but in interpretation. The isotopic fingerprints of grains must be matched with stellar models. Here, astrophysicists and cosmochemists collaborate, linking laboratory data with simulations of red giants, supernova, and neutron star mergers. The dance between observation and theory grows intricate when isotopes defy prediction models. Must adapt. Pre-solar grains thus become laboratories for testing nuclear physics itself, pushing models of stellar interiors to their limits. Particle accelerators such as CERN's Large Hadron Collider also play a role. While their collisions cannot recreate stars, they can probe nuclear reactions, cross-sections, and decay pathways that shape isotopic abundances. By understanding how nuclei behave under extreme conditions, physicists refine the nucleosynthetic models needed to interpret presolar grains. In this sense, the memory of suns is studied both in meteorites and in machines that smash protons at near light speed. Quantum technology is also entering the field. Quantum sensors promise unprecedented sensitivity in measuring isotopic ratios, detecting anomalies invisible to current methods. Quantum computers, though still in their infancy, may one day simulate the quantum complexity of stellar nucleosynthesis, offering new predictions to test against the stones. The convergence of cosmochemistry and quantum science signals a future where the smallest particles of memory are matched by the most advanced tools of thought. And yet, for all the precision, there remains humility. Each new instrument, each mission, uncovers more complexity. The stones do not yield all their secrets easily. Instead, they remind science that the cosmos is vast, its memory intricate, its story unfinished. Tools sharpen the vision, but the mystery deepens with each step. Ongoing testing continues across the globe. Laboratories in Washington University in St. Louis, at the Max Planck Institute in Germany, at NASA's Johnson Space Center, and in countless others, analyse presolar. Grains with growing sophistication. Each lab contributes pieces of the mosaic. Each measurement adds to the chorus of stellar voices carried by the stones. As techniques advance, scientists dream of mapping the galactic stardust cycle in its entirety, tracing grains from their stellar birth to their planetary resting place. Could a complete picture emerge, showing how suns die, how their ashes drift, how they seed new worlds? The goal may be distant, but each grain analyzed brings it closer. In this effort lies a profound truth. Science itself becomes a bridge between memory and meaning. Instruments are not merely tools. They are extensions of human curiosity, lenses through which matter speaks. The stones remain silent, yet in their silence they invite us to listen, to measure, to interpret. In building machines that can read their memory, humanity extends its own. The work is painstaking, meticulous, often slow, but it is also luminous. For in the laboratories, beneath the beams of synchrotrons, within the chambers of spectrometers, the memories of suns come alive once more. Each isotope measured is a note in a cosmic symphony, each grain mapped to stanza in a poem billions of years old. Science, in this sense, is not only analysis, it is remembrance, and so the testing continues. Stones fall, grains are found, instruments refine, missions return. The universe yields fragments of its past, and humanity bends closer, straining to hear. One day, perhaps, the memory carried in these stones will be fully understood, or perhaps not. Perhaps their silence will always exceed our questions, their memory deeper than our reach. But whether solved or unsolved, the effort itself is revelation. For in the act of studying stardust, humanity remembers its own origin. The stones that hold the memory of suns are not only records of what came before, they are reminders of what we are. Fragments of fire, travelers of dust, seekers of memory. The stones lie silent in our hands. They are dark, unassuming, sometimes no larger than a fingernail. Yet within them burns a story more vast than oceans, more ancient than mountains, more enduring than civilizations. They are the memory of suns, preserved not in words or symbols, but in atoms. They remind us that the universe does not forget. It records itself in matter, carries its history in elements. inscribes its journey into the crystalline lattice of dust. To touch such a stone is to reach across billions of years. It is to feel the residue of stars that lived, shone, and died before the sun itself was born. It is to hold a fragment of the galaxy's autobiography, written in the only language the cosmos has ever spoken. Fusion, collapse, explosion, survival. In these stones we meet the paradox of permanence and fragility. They are fragile enough to be shattered by a hammer, yet strong enough to endure the death of a star and the birth of a world. What does it mean, then, that such stones exist? It means that matter is not mute. It means that atoms are not simply building blocks, but witnesses. Every grain of Preseler dust is both matter and memory, both substance and story. When we measure isotopes, when we plot their ratios on charts, we are not only performing science, we are listening to testimony, we are reading the diary of the stars. And what of us? Are we not made of the same material? The calcium in bones was forged in the heart of a dying star. The iron in blood was born in the cataclysm of a supernova. The oxygen that fills our lungs was exhaled by red giants. Our very bodies are living stones, carrying within them the memory of suns. When we speak, when we dream, when we wonder, it is the universe remembering itself through us. The philosopher might say that memory defines identity. Without memory, there is no continuity, no self. If this is true, then the universe has an identity. Its memory is written not in neurons, but in nuclei. The cosmos is a being whose autobiography is matter itself. Each element is a recollection, each meteorite a chapter, each star a verse. In this way, the stones that fall to earth are not anomalies. They are the universal mind, made tangible. But memory is also inheritance. The stones remind us that we are heirs to a chain of suns. Our blood carries the decisions of nuclear furnaces. Our lives are possible because ancient stars chose, if choice can be the right word, to die and scatter themselves into space. The inheritance is both physical and existential. To know that we are made of stardust is to know that death, too, is creation. That the end of one form is the beginning of another. That nothing is wasted, nothing forgotten, nothing truly lost. There is humility in this recognition. For while we look to the stones to learn of stars, the stones also look to us. They ask, "What will you do with the memory you carry? Will you treat it as curiosity or as responsibility? If the universe has entrusted its story to matter, then we, who are matter made conscious, are its readers, its interpreters, its caretakers. We are the ones who must keep the memory alive. Perhaps the most haunting thought is this: if stones can remember suns, perhaps memory is not a feature of life alone. Perhaps it is a feature of existence itself. Every atom is a record of its interactions, every structure a fossil of its past. The universe is an infinite archive in which nothing is erased. Entropy scatters order, but in scattering it writes. Even in decay, there is inscription. In this view, time itself is memory. The arrow of time is the pen, matter is the page, and the universe is the book that cannot close. This reflection leads to a more unsettling question. If matter remembers, can it also dream? Pre-solar grains survived the chaos of stars and the violence of creation. They were carried across the galaxy, through void and shockwave, through collapse and rebirth. They endured, silent but not passive. Is endurance itself a kind of dreaming? A persistence beyond reason? A will to carry forward a story? If so, then the universe is not merely remembered by us. It remembers itself, and in remembering, it becomes aware. For awareness is not only the capacity to experience, but the persistence of experience across time. The stones are the universe's continuity. They are its bridge across ages. In them, the cosmos holds on to itself. There is a final paradox in this thought. The stones that preserve the memory of suns are not rare in the grand scheme. Every star that dies scatters its ashes. Every galaxy is filled with dust. Yet for us, here, now, they are precious. We cradle them in laboratories. We measure them with instruments. We treat them as sacred relics. Their value lies not in rarity but in recognition. They remind us of who we are and of what the universe is. And so the stones become mirrors. When we gaze into them, we see not only stars, but ourselves. We see that we are part of the cycle, that we are fragments of the same memory, that our lives are brief but not separate. Our breath is the exhalation of ancient suns. Our heartbeat is the echo of stellar death. Our existence is the continuation of a story older than Earth. The haunting close is this: perhaps the universe never forgets. Perhaps every atom is a word, every grain a sentence, every star a chapter. Perhaps there is no such thing as silence, only memory unrecognized. And perhaps, in holding these stones, in listening to their silence, we begin to understand. The stones that fall from the sky are not accidents. They are messages. They are the cosmos reminding us of its history and of our place within it. They are the stones that hold the memory of suns. And as long as they endure, so does the memory of the universe itself.